You might remember from 5.1, important velocity or important area under curves fact number 1 was that if velocity is positive, then the area under the velocity curve gives distance traveled. And I know it's easy to forget that first part, if velocity is positive, and start to just associate area under the velocity curve with distance traveled. But we have to start to understand now, and I know many of you have been anxious for this bit of information for a while, what does it mean if the velocity is sometimes negative? Well, we said that if velocity is positive, motion is forward or in a positive direction, whatever, towards something, whatever we choose to define. If velocity is negative, that means motion is backward. So imagine that saying 2 steps forward, 1 step back. If you take 2 steps forward and 1 step back, if you're wearing a Fitbit, the Fitbit counts that as 3 steps because it doesn't care what direction you're going in. It just is counting how much work you're doing, how many steps you're taking. But if you take 2 steps forward and 1 step back, you only end up 1 step away from where you started. So the difference between those 3 steps that it felt like you took and the 1 step, which is where you ended up relative to where you started, that's the difference between total distance traveled and displacement. So here's an example. If we have a graph here, this blue graph is the velocity graph for a bee that is going toward a flower, stopping and collecting pollen, going back to the hive, goes forward toward the flower, and then back toward the hive, but it doesn't make it quite there. So if we wanted to talk about the total distance traveled by the bee, how many steps would the bee get counted on his Fitbit if it were wearing one, or its pedometer? So we count the area under the velocity curve and then treat all the areas as if they were positive and add them up. So if I ask the total displacement of the bee, that's let's see, this 200 feet plus this 200 feet plus this 200 feet plus this 100 feet. The total distance traveled is 700 feet. But now if we talk about the displacement, where does the honeybee end up relative to where he started? Well, he started at the hive, he went 200 feet toward the flower, and he came 200 feet back, he's back at the hive. So his displacement so far is 0, he's back where he started. 200 feet toward the flower, and then he's at the flower, but he's going 100 feet back toward where he came from. So his displacement is 200 minus 200 plus 200 minus 100, 100 feet. So this, I think it might even be better to say, it's 100 feet in the direction of the flower. So 100 feet toward the flower from where he started, or positive 100 feet if we're counting motion toward the flower as positive. All right, so here's the information you've been waiting for. Area under the velocity curve gives what we call displacement. That's the change in the position of the object relative to where it started. So displacement takes into account the fact that some motion might be forward, some motion might be backward, and those would cancel each other out. So maybe like the bee moved away from the hive, but then back toward the hive. Those positives and negatives cancel out. Short story, in order to find displacement, integrate the velocity function with the appropriate limits. If, however, you want to find total distance traveled, that's the same distance that your speedometer, that your odometer, your Fitbit, or your step counter would count. So one way to compute it is to find the integral for the appropriate limits of the absolute value of the velocity function. Or, if, for example, you don't have a calculator, you can find the intervals on which velocity is positive, integrate those areas will be positive and you can add them up, and then find the places where the velocity is negative, integrate those, and take their absolute values. That's a way to add up the absolute values of all those areas, and counting all of the areas, the positive and negative ones, as if they were positive. And then just one more time, if you're asked to write an expression for the total distance traveled by an object, that's this expression here. It's the integral from a to b of the absolute value of the velocity function. Here's a super quick example. If this is a graph of v of t, and I asked you to find the displacement of the whatever it is on the interval 0 to 5, you would add up those areas, which add up to 1.5. You'd subtract away those areas, which add up to 2.5, and you get a displacement of -1. That would mean the particle, the honeybee, the squirrel, whatever it is, ends up 1 unit to the left of, or behind, or below wherever it started. But if I asked you to compute total distance traveled, this should say total distance traveled, that's going to be this 1.5 plus 2.5. So the absolute value of 1.5 plus the absolute value of 2.5 to make this 4. And there's a little note here. I would bet you $100 there's going to be some kind of velocity or position graph on your free response section, and you're going to have to analyze it. One more super important fact is down here at the bottom of your page. An object's ending position is its initial position, so wherever it started, plus its displacement. You would never use total distance traveled to help figure out ending position. Position is all about where you started and then what changes happened. So initial position plus displacement. Let's try this problem from your book. All right, so we have been given a velocity function. We've been asked part A to find when this particle is moving to the right, moving to the left, and stopped. So motion is to the right when velocity is positive, motion is to the left when velocity is negative, motion is stopped when velocity is 0. So what I need is a sign graph for velocity. So this is v of t, and that's lucky because I have v of t. So I start by figuring out what values of t would make velocity 0. Well, look at this. This 6 isn't going to change the value of the velocity, well, whether the velocity is 0 or not. I need the sine of 3t to be equal to 0. Well, that's going to be equal to 0 when 3t is equal to something that sining would make 0. So sine of 0 is 0, so 3t could equal 0. Sine of pi is 0, so 3t could equal pi. Or sine of 2 pi. 3t could equal 2 pi. Well, that one's easy enough. Gives me t equals 0. This one gives me t equals pi over 3. And this one gives me t equals 2 pi over 3. But notice I've been given this set of limits, which tells me that I only am interested in time values between 0 and pi over 2. So velocity is 0 when time is 0. Velocity is 0 when time is pi over 3. And pi over 2 is sort of my upper limit. Now I'm going to make a sign chart, so I need to figure out when, for each of these sections of the velocity function, for each of these sections on the number line, is velocity positive or negative? Well, velocity is, if I just, for example, plug in here pi over 4, sine of 3 pi over 4 is the y value. This is positive, and this is negative. So that's my write-up for my final answer for part A. Motion is stopped at time t equals 0 and t equals pi over 3. Motion is to the right when velocity is positive. That was on the interval 0 to pi over 3. And motion is to the left when velocity is negative, which is on the interval pi over 3 to pi over 2.